Hi, this is Chrisferb, and I'm going to review a confidence interval problem where we are determining the sample size required for a confidence interval for a proportion based on our inputs. Okay, we'll get started. An account manager is interested in estimating the proportion of a client's customers who like a new online advertisement. She wishes to develop a 90% confidence interval estimate within plus or minus 0.05, so about 5%, of the true population proportion. What sample size is required? Now, in this case, there's two alternatives for what our p-value is going to be. And that's because we don't have a population proportion already. Now, you could do a study and then you get a sample to get that, and we're not going to do that. The other accepted method is you use a 0.5 or about a half value for your population proportion, and that's considered conservative. So that's what we'll do. Okay, so this is it's not very hard. It's kind of a plug in the values type of formula, but we'll first write down what we have. So we know that we're dealing with 90% confidence interval. And for us, what that means is we're going to have to look up the z. So we're going to go and we're going to look up the z value for that. It's actually the z-score that we're going to get. And so the z-score for 90%, many of you may know what it is. Now, I use what I would consider an annotated alternative z-score table. I made all the annotations on it in this alternative, meaning it's just one half of the standard normal curve. Now, what we're going to do is we want to look up the value that would be acceptable for 90% confidence interval. And I have it written right here, 90% confidence interval. I'm going to zoom in and I'll show you how that works. Now, these files are going to be available in the comments section. So it says 90% confidence interval. It says 1.65z, and then it shows how the value is obtained. So we go and we follow this up, and this is our 0.4505. And when we go and we look at it, it says 1.6, and then we go 1.6, you can see my finger, 1.65. And that's how that works. Okay. So it's 1.65 is our z-score. 1.65. Okay. And I'm going to back this out again. Okay. Okay, so we have our z-score, and that's very important there. Okay. And then we have our error. And our error in this case is 0.05. So that's how much error we want, and the error with the z-score plays into how large the sample needs to be. Okay, and then we have those two options which I mentioned, and we're going to use the p, which is 0.05. As I mentioned before, you do a pilot sample study to compute the p-bar, but we're not going to do that. Okay, so the actual formula is this. So we have our z squared, and then p, 1 minus p, which if you've ever looked at any of my binomial probability distribution videos, it's very similar. This 1 minus p, it might remind you of our q, which is essentially the inverse of the p, which is what they're doing here. Okay, and then our error squared, we're going to square that error. So what this does is it works out to this. Not a very hard formula. Make sure you put the parentheses around the certain parts when you're using your calculator. So 1.65 squared multiplied by 0.5, and then 0.5, and then 0.05. That's our error value. A little bit of a bad looking 5, and then squared. And to save you the calculations here, we'll just calculate a couple of them. It ends up being 0.68, looks like 0.6, and then 0.0025. Then we bring this around, and our results are 272.25. And now we have to consider what our answer is here. Now this is a sample size, so we can't have 2.7, 2.25. We can't have a fraction here. So what we have to do is we have to round up. I usually don't recommend rounding, but in this case, when we're determining sample sizes, we have to round. So it's going to be 273. And that's the required sample size to make sure that we have at least 90% confidence interval with an error of 0.05 and the p of 0.05. And this is an estimate that is conservative. So that's how you would do it. Thank you for watching.